Okay, so let's move on then. Section 2.5, linear functions and their models. That should also be pretty easy. So linear functions, the slope and the rate of change, and making and using linear models. Okay, linear functions. Linear functions, something we're very familiar with. We've worked with it quite a bit by now. So a linear function is a function of the form f of x equals to ax plus b. We can also re-express that in our sort of traditional form of y equals ax plus b. Right? So any linear function will fit this form. Typically, we use the value ax plus b instead of mx plus b, where we're just used to, or most of us were probably introduced to linear equations with the variable m for slope. Right? So we have y equals mx plus b, but m and b are just any real numbers, so we can also replace it with ax plus b, where the a is the m. Good. So a is the slope, and 0, comma b is the y-intercept. Determine whether the given functions are linear. Okay, all we have to do is manipulate them and see if we can get them to fit this form, and if they can be, then they are linear. So this should be pretty easy. Let's go back to blue here. For this one, all I have to do is swap them around using the commutative property of addition. We can flip these around. The order doesn't matter. So that's 3x plus 2, and now it fits exactly that form. This is the a, and this is the b. Maybe I can just change that guy around. That will make it easier. Let this a equal to 3, and therefore the b equals to 2. Okay, over here we're going to have to distribute. We're going to have to distribute there and distribute there and move things around a little bit. So the distribution property gets me to say that this is g of x equals to 3 minus 6x. And now if I just switch those around, I'll end up with minus 6x plus 3. And again, we have that this guy is my a equals to negative 6, and the b equals to 3. So these are both linear. Okay, moving on over here, now we're going to have to simplify this. So distribute there, and then we'll end up with h of x equals 4x plus 3x squared. As soon as we see a square there, not linear. Okay, this one, all we have to do is separate this into two separate fractions and reduce. So this one we can simplify as k of x equals to 1/4 minus 5 over x over 4. So separate it into two separate fractions. And then we can move it around and simplify it a little bit more and say that this is k of x equals to 5 over 4x, negative 5 over 4x plus 1/4. And now we have our values of a equals to negative 5 over 4. And our value for b equals to 1/4. Pretty easy, right? Good. Let's see what the author did here. Yeah, moved it around. So it is linear. Value of a is 3. Value of b is 2. Distribute. Good. Separate. Good. Okay, so that's what the author did. Slope as a rate of change. Let f of x equal to ax plus b be a linear function. If x sub 1 and x sub 2 are two different values for x, and if y sub 1 equals to f of x sub 1 and y sub 2 equals to f of x sub 2, then the points x sub 1, y sub 1, x sub 2, y sub 2 lie on the line on the graph of f. Okay, that's a whole lot of messy stuff. So all they're saying is if we have, just draw like a visual representation of what all this means. If we have our Cartesian coordinate system, which is really ugly here. So we're sticking to the x-axis, the y-axis, and now we have two different values for x1 and x2. Okay, so we're saying if we have some random line, and again, this is just a random description of it. So this is going to be f of x equals to ax plus b. So now if we have a point here which is x1, then this maps to f of x1, which we're also calling a y1. And then if there's some other random point over here, x sub 2, which is another instance of an x value, it comes up and maps to this line, which comes across and maps to this line, which we're calling y sub 2, which is the same thing as f of x sub 2. Good. Okay, so then this point right here is the point x1, y1, and this point is the point x2, comma y2, which we can also say that this one is x1, comma f of x1. Right? All the notation is the same. Sometimes it's better to write it down this way. Sometimes it's better to write it down this way. Same thing with this one. We can either write it as x sub 2, comma y sub 2, or we can write it as x sub 2, comma f of x sub 2. Okay, that's what this whole thing was trying to describe. And of course, these are the these two order point pairs are points on the line. Okay, so from that whole description, we can say that the average rate of change between the points x1 and x2 is the same thing as the slope of the line, which is going to be equal to this, y sub 2 minus y sub 1 over x sub 2 minus x sub 1. Right, so sticking to this little picture to see what's good. We don't want to go with the blue. So we create a little triangle underneath it. Let's go with green. So let's say we come up with this little triangle right there. Then this distance right there, well, it's going to be the change in the y direction, delta y, which is also equal to y sub 2 minus y sub 1, which is also equal to f of x sub 2 minus f of x sub 1. Right? So whether you describe it this way, or whether you describe it this way, or whether you just say delta y, they all mean the same thing, right? Change in the vertical direction. And then here, well, this little gap here is either delta x, or you can also say it's x sub 2 minus x sub 1. Good, so the slope is rise over run, which is equal to delta y over delta x. Delta y over delta x, or y sub 2 minus y sub 1 over x sub 2, x sub 1, or f of x sub 2 minus f of x sub 1, all over x sub 2 over x sub 1. Right, no matter how you slice it, we still keep looking at the same definition for slope, which in this case is the same thing as the average rate of change. The average rate of change is equal to the slope. Then we have a linear equation. Since the average rate of change of a linear function is the same for any 2 points, it's simply called the rate of change. Right? So when we're looking at an equation that's linear, we no longer have to say the average rate of change, it's just the rate of change, which is the same thing as the slope. That's all this is pointing out. Should be a very easy section. So a dam is built on a river to create a reservoir. The water level, f of t, of the reservoir at a time t is given by this equation. F of t equals to 4.5 t plus 28, where t is the number of years since the dam was constructed and f of t is measured in feet. Sketch the graph of f. Well, that's really easy. It's just a linear equation, right? So it's just a line. The graph is a line where this is the slope. Slope is equal to 4.5. And this guy helps me find the y-intercept. 0, 28 is the y-intercept. So just as a rough sketch here, I don't have to draw a super pretty one. I know it's got a positive slope. I know the angle is going to be this way. And I go through the point 0, 28. So I don't know, maybe something like this, where this point right there is the point 0, 28. And then I can use this to find one more point on the line. Now I have to create this little triangle underneath it to do that. So I can go this way, go this way. Since it is a decimal, I could say that this is equal to 4.5 over 1. So 1 unit this way, 4.5 units that way. Or if I want to get rid of that decimal, I can just multiply the numerator and denominator by 2 and say that this is 9 divided by 2, just to get to some pretty whole numbers. And that makes it easier to deal with this. This is 2, and then that's a 9. Good. Which leads to another ordered pair that's definitely on the green line. Let's make it in green. Another point on there, which is going to be the point 2, 37. Okay, what is the slope of the graph? Oh, we already answered that for part B. The slope is 4.5. Oops, here I got used to the x and y thing here. So this isn't the x-axis. It's the t-axis. This is t, and this is f of t. Okay, slope is 4.5. The rate. What is the rate? At what rate is the water level in the reservoir changing? Its rate is changing at this, right? It's changing at 4.5. Is this in feet? T is the number of years since the dam was constructed, and this is in feet. It's changing at a rate of 4.5 feet in 1 year. Or as we did before, we can change this to a 9 over 2 by multiplying both numerator and denominator by a 2, or 9 feet per 1 year. Oh, sorry, for 2 years. Right, so here's a better graph of it. So this is similar to what I did, only a little bit better, which means that this point right here is the point 0, 28, 10, 20, 30, so right below the 30. So this is 0, 28. And then if you go out 2 units this way and 1 unit up, we get to the point 2, 37. Okay. And then the graph has a slope of 4.5. So the rate of change is 4.5, the coefficient of t, since the time t is measured in years and the water level is measured in feet. Then the water level at the reservoir is changing at a rate of 4.5 feet per year. Right? Or we can change it. It's nice to leave it as a per year statement. So if you want to leave the decimal 4.5 feet per year, that sounds like something we can manage. Or we can change it into 9 feet per 2 years, or 9 feet every 2 years would be the other way of describing the same thing. Since the rate of change is positive, it means that the reservoir is rising. Making and using linear models. Okay, when a linear model is used to model a relationship between two quantities, the slope of the graph of the function is the rate of change of one quantity with respect to another. So here we have an example where we have time in the horizontal axis, and in the vertical axis we have volume of gas. So maybe you're filling up your gas tank and you're checking to see how fast it is filling up. So in a time span of 3 minutes that goes by, 6 gallons were added to the tank. It seems pretty slow. So the rate of change, and it's linear, so we don't have to say the average rate of change, since we know that for any 2 points, when we find the average rate of change, they're all going to be the same. So we just say the rate of change. So the rate of change that's happening here is 6 gallons filled over a time span of 3. This is delta y over delta x, or about 2 gallons per minute. Or we can also have this graph. Maybe this is how slowly it's being drained as you're driving, perhaps. So as you're driving and you're using up your gasoline, here is in the horizontal axis time spent driving in minutes, and then on the vertical is the volume of gas remaining in your tank. So it looks like we started off with 18 gallons. That might be the full capacity of your tank. Maybe it's a full tank. Doesn't necessarily mean that though. Maybe it's much bigger, but you didn't start off with the full tank. But at any rate, you started out with 18 gallons of gasoline. And slowly, as the minutes progress, the volume starts to get smaller and smaller and smaller. At timestamp 100 minutes, you had 15 gallons. And then 100 minutes later, at timestamp 200, you were down to just 12 gallons. So you lost 3 gallons, negative 3 gallons, in a gap of 100 minutes. So if we divide those two things, negative 3 divided by 100, negative 3 divided by 100, that's how you get that this negative 0.03, negative 0.03 gallons per minute, right? So this is like earlier when we had a decimal, we had a 4.5 gallons per minute. So we could handle 4.5 gallons per minute. We can visualize what that means. But 0.03 gallons per minute, that it's being drained at this rate. That's a little bit more difficult to visualize. So in a case like this, you might actually want to leave it in terms of whole numbers and say that you're draining at a rate of 3 gallons per 100 minutes. So that could be, it's just a personal choice, whether you want to describe it in one way or the other. But it's just compact to say gallons per minute instead of saying 3 gallons per 100 minutes. 3 gallons per 100 minutes. Right, and this is drained. So we want to throw that word in so that we know that this is going down. It's being drained at a speed of 3 gallons per 100 minutes. Or, like we wrote up here, we can also just write it as drained at a rate of 0.03 gallons per minute. Good. If you don't want to use the word drained, then you can throw in that little minus in front so that people know that you're going in the negative direction. Okay, so here's an example. Water is being pumped into a swimming pool at a rate of 5 gallons per minute. Initially, the pool contained 200 gallons of water. Find the linear function v that models the volume of the water of the pool at any time t. Okay, so this is really easy. We have the volume v of t is going to be some sort of an equation as a function of t. And we know that it's got a speed, an average rate of change. So every minute that goes by, we're going to be adding 5 gallons. So it's going to be 5t plus the initial amount, plus 200. Right, so this one was really easy. We can just kind of put it together on inspection here. But if you really wanted to put in some work to this, then you'd kind of go back to basics and think about v of t as a general equation, which is a t plus b. And you need to figure out that the value of a is a 5. And from the information, figure out that the value of b equals to 200. So if you wanted to put in some work, you could. Right, this is, well, there's no real work in noting that the value of a is a 5. The fact that the 200 is the initial amount means that when we graph this, we want the input value of t at time 0 to be equal to 200. So we have the ordered pair 0, 200. Right? At time 0, time equals to 0 means that the volume equals to 200, where we started off. Okay, so we end up with the same equation. So if the pool has a capacity of 600 gallons, how long will it take to completely fill out the pool? So for part B, we need to figure out when this equation equals to 600. Okay, so we have v of t equals to 5t plus 200. And so we want to find t such that 600 equals to 5t plus 200. Right? 600 is the volume. Don't confuse that 600 to be a value of t. It's the volume. We want to know when the volume will reach 600. So this is a simple equation to solve. Minus 200 on this side, minus 200 on this side. we end up with 400 equals to 5t. Divide both sides by 5. We get 400 divided by 5 equals to t. And that's because this divided by 5, this divided by 5, this has cancel. Good. So t equals to 80. Good. I think that's in minutes. So per minute, 5 gallons per minute. Okay, so it'll take them 80 minutes to fill out the whole thing. It'll take 80 minutes to fill the pool.